Hi, I'm Alfonso Lagares, a student in Professor Fenton's Physics 2211 class, and this is my Lab 3 report where I'll be finding the mass of a black hole. First, I'll introduce the concept of gravitational force and its importance. I'll then briefly discuss how to find the parallel and perpendicular components of a force, and then I'll analyze the model used to find the unknown mass of a black hole. Finally, I'll give a short conclusion and evaluation of the lab. This lab focuses on objects that experience gravity. Gravity is an attractive force that naturally appears between matter, pulling it together, and is directly proportional to the mass of the two objects being attracted to each other. It is also inversely proportional to the square of the distance between the objects. Gravity plays a fundamental role in macroscopic processes, being the most important force in the movement of planets and stars. In this experiment, we will find the mass of a black hole using the value of the gravitational force experienced by the star orbiting it. This force can then be used to find the mass of the black hole, rearranging the formula for gravity. In this lab, I'll also calculate the parallel and perpendicular components of the force of gravity. These two components of the force will be parallel and perpendicular to the trajectory of the object and are calculated using these formulas. The parallel component of the force points parallel to the star's motion and is tangential with the kissing circle. The perpendicular component of the force points perpendicular to the star's motion towards the center of the kissing circle. Going on to the model, I used the GlowScript script to simulate the movement of a star around the black hole of unknown mass. The star was given a mass of 2 × 10 to the 30 kilograms, and a random trajectory was generated for it using my Georgia Tech email as a seed. This yielded a list of coordinates describing the motion of this star around the black hole. The time between data points was also set to be 1 day, or 86,400 seconds. This model assumes no other gravitational interactions exist, other than the one between the black hole and the star. Using these initial conditions, I calculated the initial and final velocity of the star at every point of the trajectory. I also calculated the initial and final momentum vectors by multiplying the velocity of the star by its mass. Finally, I also calculated the change in velocity and momentum. I then moved on to calculating the rate of change of momentum experienced by the star by dividing the change in momentum by the time difference between data points, delta t. Applying Newton's second law, I calculated the net force acting on the star. I then proceeded to decompose this force into its parallel and perpendicular components. I first calculated the unit vector of the initial momentum, followed by the rate of change of the magnitude of the momentum. Multiplying these yields the parallel component of the rate of change in momentum. This rate of change in momentum in the parallel direction is equal to the net force in the parallel direction, following Newton's second law. The perpendicular component of the rate of change of momentum was then found by simply subtracting the parallel rate of change of momentum to the rate of change of momentum. The perpendicular component of the net force was then found applying Newton's second law. Finally, I used the net force to find the mass of the black hole. This mass was slightly different for every point of the trajectory, but averaged out to be 1.2 × 10 to the 34 kilograms. In conclusion, the model accurately predicted the mass of the black hole given the trajectory of an orbiting star. Regarding the difference between change in momentum and net force, you can observe the measured changes in momentum by measuring the change in velocity and mass of an object, but net force cannot be measured directly. Thus, you must assume that the change in momentum of an object is the result of the net force acting on it. If the black hole the star was orbiting around was replaced by another body and the trajectory of the star did not change, it would be impossible to tell the difference, as the trajectory of the star only depends on the mass of the black hole. The mass of this new object would be calculated and would be found to be equal to the mass of the previous black hole.